Precalc chapter, point 4. It's the nth roots and real exponents. So the nth root there, as we have that box, obviously on the screen, it's a little bit smaller than maybe we would like. Let me see if I can move this a little bit closer. Yes, it's trying to zoom. Okay. That's about as big as it's going to get here. Again, you guys can look this up on the outlines on Haiku. So basically, if I was to ask you what's the square root of 25, you guys would tell me what? Maybe tell me 5. If I ask you the square root of 49, it's 7. Okay? Why? It's because 7 times 7 is 49. So what it has here is that if a and b are real numbers, and you let n be any positive integer greater than 1, it shows that if a is equal to b to the n power, the b is the nth root of a. What? Well, you said 49. Shall we write that down? 49, bless you, is 7 squared. So what's the square root of 49? 7. Because it's 7 squared. 7 squared makes 49, so 7 is the square root of 49. What is the cube root of 8? 2, because 2 to the third power is 8. In other words, what times itself 3 times is 8. 2. Now, I was asking you guys the square root of 25, and you said 5, square root of 49, 7, because that is what we call the principal square root. The principal square root is the one that has the same side as the number that we are taking the square root of. Or the sign, yeah. So most of the time, it's always positive, because we're asking positive, square root of positive 25. That's positive 5. So you got to be careful, though, because when we solve equations, wouldn't you guys also agree that negative 5 times negative 5 is also 25? So we have to kind of be careful on there. Okay, so I've got a question. What's the fourth root of 81? Fourth root, 81. No calculators. It's 3. How did you get 3?
Oh, is it 4 times 1?
No, it's 3 times 3 times 3 times 3. 3 to the fourth power is 81. What times itself 4 times is 81? Well, you can start with 1. 1 times 1 times 1 times 1 is 1. 2 times 2
4
times 2
is 60.
8 times 2 is 16. So it can't be 2, so then you try 3. 3 times 3,
9. 27.
times that by 3,
27.
and times that by 3.
It's a bigger number, 56 or something.
It's 81. Okay? And then we have this box here, this chart. I'm going to start with the right side of the chart. It says, suppose n is an integer greater than 1, and a is any real number. So sticking to the right side there, it's using this thing. We don't write it, it's not on here, but I'm using the nth root of a. Okay? If n is odd, 1, 3, 5, 7, 9, 11, la-di-da-di-da, and a can be any number it wants to be inside. But, as you can see, I'm going to talk about not only is it being odd, over here on this row, this first top row says that the number inside has to be positive. What it says is that there will be 1 positive and no negative real roots. Well, okay, that makes sense. What's the cubed root of 8? 2. What's the cubed root of 27? 3. What's the cubed root of 64? 4. There's one answer. You didn't tell me plus or minus, right? But then we go to the next row down, and it says that if a is negative, it has no positive answer, but has one negative real root. So like the cubed root of negative 8 is 8 times itself 3 times is negative 8. It's negative 2. Because negative times negative is positive, but then there's another negative which would make it negative. 3 negatives make a negative. Careful. When we're multiplying. Well, if we were adding the negatives, then it would be negative. If we are subtracting negatives, then we'd be positive. Ooh, that's interesting. Okay, now, we're going to move to the bottom row, which I think should just be a universal box between both of them. And it says that, hey, I don't care if I'm taking even or an odd root. Any root of 0 is 0. 0 to any power is a 0. And then I'm going to work my way back up here, or on back to the top. If n is even, 2, 4, 6, 8. Okay. Now, if we talk about, say, the square root, and the number inside that square root is positive, we will have one positive and one negative answer. So technically, if I ask for all the roots of the square root of 25, it's plus and minus 5. Because negative 5 times negative 5 is 25 as well. And here's a cool thing. If that number inside the square root, or even root, is negative, you just state no real solution. I'm not having you find the complex. You don't have to poke an eye out, okay? Today, just say, no real solution. Think we can handle that? I have some examples for us. What is the negative square root of 49? What am I looking for? Okay, I heard plus or minus 7. I also heard negative 7. Oh, well, we had to throw that one out, so now we had to say 7. Which one is the correct answer? So we should. So I think we get a little bit of everything here in these camps. But
Wait, what?
isn't order of operations tell you to do the square root first?
Yeah.
Yes.
And what's the square root of 49? 7. But according to that chart, 49 is a positive number, so it should actually be plus or minus 7. Unless we're talking about the principal square root. Oh, man.
Well,
So say we're not talking about that principal square root. What if it was plus or minus 7? But now you have a negative out front. And you're like, okay, a positive 7 with a negative out front would be negative 7. Then if it was a negative 7 and we put the negative on front of it, now all of a sudden negative negative makes a positive 7. So shouldn't it be plus or minus 7?
yeah.
Unfortunately, it's not.
Oh.
It is not the plus or minus 7. It is the negative 7 because that's the one it wants. It wants the negative square root of 49. So, in this sense, act like you're asking for the principal square root and make it negative.
So can we just say like the outside sign just goes in front of the thing?
You would take the principal square root of 49. So you have to do square root of 49 first, 7, and then make it negative.
Because the sign's just there.
Well, it's really like a negative 1. So it would be negative 1 times 7. The next one, cube root of 64 over 27. Who remembers the properties with square roots? Or roots on a fraction?
Both of them get
I
it.
think I
Both of them get it, or you can split it to the top and to the
Bottom.
bottom. So that means I should have the cubed root of 64 over the cubed root of 27. Then you just have to ask yourself, what's the cubed root of 64? Oh, it's 4. Cubed root of 27? Your answer is?
4/3.
No, wait a minute. Because all odd roots only have one solution. Cool stuff. And what about the fourth root of negative 121?
Couldn't be.
Couldn't be, so therefore we say no real solution or no real numbers. I told you guys, if you're taking an even root of a negative, just say, hey, there's nothing real here. And you're good to go.
Wait, is that a 4?
That's a fourth root of negative 121.
I'm lost.
Part B already used some of this. So that was the second one, the quotient property, that says that if I have the radical, the root of a number, and divided by the same type of root of another number, I can put them together in the same root. But this is a two-way street. That means that if I have a root of a fraction, I can split them to their own. We already used to use that property. The same thing goes with multiplication. If these roots are the same, I can take the numbers and multiply them together. And vice versa. If there's two numbers multiplied together inside the same root, I can separate them to their own with multiplication. We've been using this when simplifying square roots, guys. We've used this a couple times. And so for the next couple examples, I'm going to show you both ways. I'm going to show you the proper way using this terminology and that whole idea then of going to the dance. Because going to the dance uses the rules but without having to state every single thing. Okay? Can I turn the channel? Or page here. Turn the channel. We are turning to channel 8. Okay. So, here's our examples. I want you to simplify using the absolute value. Well, using the absolute value if you need to. We're forgetting about that part for now. If I have the 6th root of n to the 18th power, and I want to simplify this, I can use rule number 1. Rule number 1 says that if I got numbers that are multiplied inside, I can separate them to their own root. How many n's are there in there?
18.
There are 18 of them. So could I take that as the 6th root of n times the 6th root of n times the 6th root of n times the 6th root of n, how many times? 18 times. Or, wait a minute, could I set it up so that the power on n and the root there will be the same so they cancel? So if I, by chance, wanted to write n to the 6th power but have the 6th root on it, those would cancel each other and leave me with n. But that only accounts for how many n's? 6. I have to account for 18 of them. So isn't that the same thing as doing it again? Now I have 12, and I can do it again. Because n to the 6 times n to the 6 times n to the 6 is n to the 18, because you add exponents. Yeah? Now remember, these cancel. So this is gone, 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 leaving me with n times n times n. To be n to the 3rd power. We could do a couple different things. There are multiple answers to this. 18 is 3 times 6, or 6 times 3. So you could play with your exponent rules and also get the same thing. Not this particular word, no. Now, guys, if I was going to my sixth root dance, my sixth root dance would follow this idea. Oh, not third, but six, right? You can't see it on the screen. It's jumped off your screen there. But that's the sixth root of a very large house. Because inside this house, I am going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, I said that. Now, I'm not looking for partners to go to the dance. I need groups of 6.
That's a big group. Did you need 18 people?
No, I'm taking groups of 6. Right there. 2, 4, 1, 2, 3, 4, 5, 6. And 6. How many groups of 6 are there? And each one of those groups, remember, joins up and they become 1. So therefore, n times n times n, which is n to the third power. That's how my reference, guys, going to the dance. Notice that I grouped them up into partners of 6, which would really be n to the 6th power, which would have the 6th root on it, which would cancel, leaving you with n, n, and n to get n cubed. So it's the exact same thing without having to show the breakdown of the 6th root, 6th root, 6th root, or square roots sometimes. Now, can you guys apply either one of those rules, or maybe a mix of those, to do problem B? Try it on your own. Okay, guys, to save a little bit of time, I highly suggest you do not try to multiply the a plus 1 to the 12th power out, because that would be a plus 1 times a plus 1 times a plus 1 times a plus 1. It's a lot of foiling, distributing, multiplying, and you will have a 12th degree polynomial. I would not do that. The hard work's already been done for you. And so, wait a minute. Is it really any difference between a to the 12th power and a plus 1 to the 12th power? I mean, there's a huge difference overall, okay, in the value that it could represent. But not in the way that you're going to use it. Think of 81. I think 81 itself can be taken apart, and then the a plus 1s can be taken apart. So my first move would be to actually separate them to their own roots. Now, I am not going to say this is the only way, but I think it just seems like this is a good break. Break those apart. You got coefficients, you got polynomial parts. And so, what you're going to want to do, is then break this down. So I'm going to use a little bit of a mix between my two methods here. So wait a minute, 81 can be broken down to a bunch of 3s. How many of them by chance? How many do I need? So all of these get to leave, they become a? No, they become all 3. Now wait a minute. This same idea can be expressed with the a plus 1s. I have how many of them? There are 12 of them, and they need to be grouped in groups of 4. How many groups would be able to leave?
3.
They would have 3, so that would be a plus 1 to the 3rd power. You're done. Or, wait a minute, a plus 1 to the 4th power of the 4th root. 4th root of a plus 1 to the 4th times another 4th root of a plus 1 to the 4th, right? Each one of those groups would represent an a plus 1. An a plus 1 times a plus 1 times a plus 1 is a plus 1 cubed. So there's a couple different ways to approach that. None of them are necessarily wrong. Now, moving on to the last problem I'm going to do here is part D. It's a fifth root of negative p to the 10th q to the 7th. I don't think we should have any problems with the p to the 10th q to the 7th. But I think we're going to have an issue with that negative 1. I think everybody would recognize that I could technically take a fifth root of negative 1, multiply that to the fifth root of p to the 10, times that by the fifth root of q to the 7. Right? That's just splitting it up. P to the 10th, how many groups of 5 can I make? 2. Would there be any leftovers?
No.
So everybody would get to leave, which means that would be p squared. How many groups of q can I make?
1.
I can only make one group. That one group would carry 5 of them. How many left over?
2, 3.
So therefore, there'd be 2 people left home. A q gets to leave, but then there's a fifth root of q squared. What about that negative 1? What's the fifth root of negative 1? It is negative 1. Now wait a minute. This is going to get crazy here. What are the factors of negative 1? 1 and negative 1. But wait a minute. Could I also do negative 1, negative 1, negative 1?
Well, yes.
Could I do negative 1, negative 1, negative 1, negative 1, negative 1?
No. No.
Wait, how many negative ones? Did you do?
5 negative 1s.
Yes.
So wait. So you're saying that I can make a party of 5 of negative 1s?
Yeah.
And if I can make a party of 5, that means who gets to leave? Negative 1 gets to leave. So when they group up, it becomes a negative 1 p squared q with the fifth root of q squared. Or you don't need to write negative 1, you put negative p squared q fifth root q squared. Okay? Negative 1 and 1 are those weird things that you can keep stacking, multiples of them, multiplying, right? And you could end up with the same thing over and over and over and over again. But basically, the odd root of negative 1, it doesn't matter which odd root, is always going to be negative 1. The last slide is talking about switching from exponent form to radical form. Essentially, you need to realize that if I have a fractional exponent, that bottom part of the fraction of the exponent is the root that is in question. So a square root will have some number to the 1/2 power. A cubed root will be 1/3 power. Yes? Okay. I would remember the second one here, because sometimes our fractions have numerators and denominators. And so you need to recognize that if I have some number that has a fractional exponent, I can use power of a power to my advantage one way or the other. Which means that I can do b to the 1 over n to the m power. Right? Because power of power says you multiply. That is the first, or the second option. No, first option here. There. But I also can do b to the m to the 1 over n, which is the second option, where m is inside on that b value. So what we should do here is on this problem is we need to think of how can I simplify roots. And if you notice, this is the 10th root of 32 over the 6th root of 2. It'd be way more convenient if the roots were the same, because then I could combine those numbers. Or if the bases were the same, it'd be way more convenient because then I'll have exponent rules. So I suggest you do is I suggest that you switch these to exponential form, which means this is 32 to the 1/10 power over 2 to the 1/6 power. Do you see common bases? 32 and 2? No. Do you see common exponent? No. Oh no. What do we do? You guys remember back last year when you guys worked with logs? And sometimes when we solved logs, we ended up trying to get the same base
So they can wipe out.
so they could wipe out. Yes. So, can 2 be written as a base 32? Probably not. But can 32 be written with base 2? Yes. Guys, the video will be completed. I'm still recording within the next 5 minutes. This last problem will be on there, and your homework will be here. So the bell rings. Now we're back at this problem. I would take 32 and make it base 2, which means 32 is really 2 to the 5th power, and that's to the 1/10 power because of power of power option, over 2 to the 1/6. Well, you need to recognize that because you have power of power, you're going to multiply, which leads us to 2 to the 5 over 10, over 2 to the 1/6. Reducing some more, I get 2 to the 1/2 power over 2 to the 1/6. Hopefully there's not too many questions on that. But now we have two bases that are being divided. We can subtract our exponents, which means it's 2 to the 1/2 minus 1/6. And to make this happen, you need to have a common denominator, which means multiply the top and bottom of the first fraction by 3. So I end up with 2 to the 3/6 minus 1/6, which is 2 to the 2/6, which is 2 to the 1/3, which if I switch it back to radical form, then it'd be the 3rd root of 2. And there's your answer. So I use exponent rules. I use the fact that I can switch between exponent form and radical form, and I was able to simplify it. So your homework is here again, page P17, 1 through 22 every 3, and I would like you to do 30 and 31. Have a great day.